Irish, if you're curious. Irish spelling for.
Okay. Welcome to the, well, it doesn't matter, New York City Category Theory Seminar. Eoin Moore is going to speak about the arithmetical completeness and soundness of the language of proofs.
All these logical proofs.
Of the logic of
First
proofs.
slide.
Error on the first
Well,
slide.
the first slide is the least read, as usual. The author.
I just want to thank you guys. I know that normally your category theory seminar starts earlier than this, and you guys made an exception for me. I was just teaching down at Baruch College, so I just rushed here to get here, so thanks for making an exception. Today I'm going to talk about the arithmetical completeness and soundness of the logic of proofs, which is written in the language of proofs. And what this means will become clear. But the story starts with Intuitionism, which was founded, the philosophy, by Brouwer. And Brouwer didn't like the traditional notion of mathematical proof, whereby you could prove statements such as P or not P without actually exhibiting a witness. So P or not P is true. He didn't like this. He wanted an idea of truth whereby to actually demonstrate that something was true, you had to prove it. And in this sense, truth is now to be equated with provability. And Brouwer has this statement: a statement is true if we have a proof of it, and false if we can show that the assumption that there's a proof of it leads to a contradiction. This is a mathematical philosophy, or philosophy of mathematics. His student Hayden attempted to take what derivations you might arrive at using this philosophy and formalize it in a logical system. And this logical system is called Intuitionistic Logic. Just as our reasoning perhaps is classified in propositional calculus, Intuitionistic logic is, intuitionism is governed by intuitionistic propositional calculus. Okay, so intuitionistic propositional calculus was developed by Hayden. It's a formalism which is attempting to describe intuitionism. And essentially, it's the law, it's propositional calculus without the law of excluded middle. Take all the other axioms. Now Gödel came along and he wanted to somehow take this non-classical notion of intuitionism and see if he could embed it in classical mathematics. He didn't want to get rid of classical mathematics. He said, truth is provable. So what happened? Maybe I could develop a calculus where provability is paramount. And he developed S4, which also was independently developed by Lewis. But Gödel developed S4, and it has these rules which you might, on first glance, think looks like some sort of logic of provability. You have, well, first of all, propositional calculus. Then you have this distribution, box, F implies G implies box, F implies box G. And I forgot to mention box F is a modality, but it should be interpreted as F is provable. So if it's provable that F implies G, then if F is provable, then G is provable. Next one, if F is provable, then F. Box F implies F. Box F implies box F. If we have a proof of F, then we can verify this proof with another proof. And rule of necessitation, if we actually do prove F, then we prove that box F. Seems like provability, but it's not quite right, and Gödel himself realized this.
Well, what's the difference between the last two?
The last two, box F implies box F.
Right.
And the rule of necessitation, I guess.
This one is internal to the theory, that this is an actual axiom of the theory,
Right.
and this is external. If you prove, if F is derived, then box F is derived.
Okay.
And
Particularly,
particularly, it doesn't lift into a context where there are assumptions. So.
Okay.
But for successful calculus, you actually need both. You need this as a rule, model calculus, and you need it internalized as an axiom. It's technicality, but it's important technicality.
Okay.
And why can box F not be read as provability? Well, to say something's provable means there is a witness, there is an X, such that proof of X in F. And well, if that were true, then use box F implies F, where F is falsum. Take the contrapositive. We have S4 yields. The negation of falsum implies the negation of box falsum, which means that S4 yields the negation of box falsum. Apply the rule of necessitation. S4 yields box negation, box falsum. Now what does this intuitively mean? Well, box, remember, means provable in a theory. So what does it say? It says our theory proves that. Our theory does not prove contradiction. And that's contradicting Gödel's second incompleteness theorem. Our theory cannot prove its own consistency. Our theory cannot prove that our theory does not prove contradiction. You see, not box falsum is consistency in the theory, so we cannot prove it in our theory.
Well, it can prove it if it's actually inconsistent.
True, if it's inconsistent.
Well,
It
you
proves everything.
said Gödel knew that there was a problem, but he called it beweis, no? He called it beweis, didn't he call it that? Didn't he think it was about provability?
Did he call S4 beweis?
No, didn't he? The box.
He did call these, he had his own provability operator in Peano Arithmetic called bev,
Right.
and we're working, so right now we're not working in PA, we're just working in an axiomatic system, a modal logic. We're supposing, could we interpret this in Peano Arithmetic? And could we interpret that as bev? And
So, but he was
Gödel
working
used, instead of box, Gödel used B.
B for
That's the only
beweis.
difference, yes, for beweis bar.
Right, so he did think of it in terms of truth.
Of course, no, it was not intention, it was intention.
This is just showing that we can't use these rules to reason about provability.
Ah,
yeah, this is showing that this, even though it has some similarity to provability, it's not quite on the money. And if you do want to have a calculus where you have box interpreted as provable in Peano Arithmetic, that problem was solved. And it was solved by Solove. And that modal logic is called GL. And I will not discuss that in this talk, but GL is when box is provable. But S4, let's not throw out S4 yet. It's still useful for interpreting IPC, and it follows from the following theorem of Gödel, McKinsey, and Tarski. Let the translation of F, a formula of F, be box every subformula. Now, IPC proves F if and only if S4 proves the translation of F. So what we have here is we have an embedding of intuitionistic propositional calculus into S4. So S4 does have something to do with IPC. Now let's look at it from another angle. We develop a semantics for intuitionistic logic. Brouwer, Hayden, Kolmogorov semantics for intuitionistic logic. And they wanted to talk about these notions of proof. What should a proof be? A proof of A and B contains a proof of A and a proof of B. A proof of A or B is given by presenting a proof of A or a proof of B. It's very intuitionistic. A proof of A implies B. Well, it's a construction. If I give you a proof of A, you can output a proof of B. And falsehood is a proposition which has no proof. Box A is, negation of A is shorthand for A implies falsehood. We could develop semantics for IPC, but they don't formalize the BHK semantics for IPC. They don't ground IPC in actual proofs. So certain semantics for IPC have been done, such as topological semantics or Kripke models, but these aren't exactly talking about real proofs. And we want to have, a la BHK, something like a real proof to ground ourselves in. Can this be done? And the answer is yes. It was proved by Professor Artemov in 1995, I believe. The slide says 94.
At that time, not yet a professor, but.
And it's called The Logic of Proofs. That's the title of this talk. It successfully formalizes the BHK semantics for IPC, and it uses an actual arithmetical notion of a real-life proof. The idea here, the key distinction between what S4 did was S4 kept track of provability, box F. F is provable. Now we don't keep track of provability. We keep track of specific proofs. So rather than box F, we will say T is a proof of F. I give you a witness for F. This specific thing is a proof of F. And in addition, I didn't mention it, but I'll mention it later, LP closes known loopholes of BHK. So there are some problems with BHK, which we'll discuss at the end, that LP addresses. So what do we have here? We have an embedding from Gödel, McKinsey, Tarski, IPC, and S4. S4 embeds into LP. This is a theorem in its own right. And LP then embeds into PA, where the embedding has a natural notion of proof along with it. And this talk is going to address that last embedding. LP embeds into PA. I'm going to prove this. I'm going to show that LP is sound and complete with respect to arithmetical semantics. And at the end, I'll discuss how LP formalizes BHK semantics. What's the rest of the talk going to look like? First, we have to introduce what we're working with, the LP language, the LP axioms. I'll define what it means to be valid and what an arithmetical interpretation is in LP. Then I'll prove soundness. If LP proves F, then F is valid. This is a straightforward induction on formula complexity. Nothing new here. Then I'll prove completeness. Completeness is the hard part of the proof. If F is valid, then LP proves F. And I'm going to prove that by contrapositive. I'm going to assume LP does not prove F. Then I'm going to produce an arithmetical interpretation where F fails. And producing this arithmetical interpretation will be laborious. And then I'll discuss LP with relation to BHK. What is the LP language? The LP language contains justification terms, which are also called proof polynomials, and formula. The terms are built with variables and constants. And inductively, from this set, we can build operations. We can build other terms with operations. We have a binary plus a binary times and a unary bang. T1 is a term, T2 is a term, T1 plus T2 is a term. Formulas, we're going to have propositional variables with capital letters. We'll have falsehood. We'll have basic connective x implies y. And we would like to connect the formula and the terms. And this is the new symbol, which is colon, T colon x. This is the key ingredient right here, T colon x. This means that T is a proof of x. That's what I want you to think. When you see T colon x, it means T is a proof of x. Remember, before we had box F, now we have T colon F, or T colon x.
So do the polynomials all go on the one side of the colon and the formula always on the other side?
No, in this formalism, then they're mixed. So we can actually have formulas that have polynomials on the inside, and then we can connect them with other formulas, and then put more polynomials attached to it.
Okay. And the term is, but the T, is that always a polynomial on the other side of the?
So this thing right here, on the left-hand side of the colon, is always a polynomial.
Okay.
Mm-hmm. But on the right-hand side is a mixture.
Okay. Thank you.
Formally, it has a type of formula, but it allows to contain terms.
Sure. Okay.
So you're right, but this provides it.
Okay.
Now, the axioms in the language, the axioms include all tautologies of propositional calculus. We actually are working in, propositional calculus here. And then we have a few others. We have application. If S is a proof of X implies...
Not just the intuitionistic ones.
Not just the intuitionistic ones, but hopefully you can see parallel to S4 here.
Okay.
So if S is a proof of X implies Y, then T is a proof of X. Then we can get a proof of Y from application. S times T is a proof of Y. This looks like box. This looks like the first axiom of S4.
I see.
Yeah.
Before we had box X implies Y, implies box X, implies box Y. Okay? So there's similarities here on purpose.
But now you're being specific to say it's S and T, not just a generic box which says there's something.
That's exactly correct. We're being specific with S and T, and specifically the way we get Y is by taking S and apply it to T. S is the proof of X implies Y, and T is the proof of X. If I take S, apply it to T, S times T, I get a proof of Y. We're seeing how we can basically internalize modus ponens with our proof polynomials. If S is a proof of X, then S plus T is a proof of X. If T is a proof of Y, then S plus T is a proof of Y. So we have a choice. If S is a proof of X, then we can actually prove that S is a proof of X via number 4, proof checker. If S is a proof of X, then bang S is our proof that S is a proof of X. And verification. If S is a proof of X, then indeed X. We want this to hold. We don't want to prove things that are not true. Additionally, we contain modus ponens as our rule of inference. And we want to be able to internalize our proofs. So LP0 is above. LP is if we have the additional axiom called axiom necessitation. For any axiom, we have a witness for that axiom. We have a proof of that axiom. And in particular, C is a proof constant. So LP proves C colon A if A is an axiom and C is a proof constant. We basically want to be able to internalize our proofs starting from axioms in LP. We can talk about a constant specification. We could add to the language additional reasoning. So let's think about it. C1 colon A1, Cn through An. If this is a set and I include it as additional axioms to LP, then this is, these are taken as our givens. One talks about LP sometimes as reasoning about reasons. And so if these are our reasons, we can go ahead and include them just a priori as axiomatic and then reason about them, see what we've developed. But I'm not going to talk too much about constant specifications this talk. We will work sometimes in a Gensen formulation. You guys have seen Gensen formulations before. It's here. It's just a way of not using a Hilbert style system. So these are all the standard rules in the Gensen system, weakening.
It's an example of a monoidal category.
Excellent. Now the rules that are particular to LP in a Gensen system, that's what the G superscript stands for, are the following. If from A and gamma I can get delta, then from T and A and gamma I can get delta. If gamma yields delta and T colon A, then gamma yields delta and bang T colon A. If gamma yields delta T colon A, then gamma should yield delta T plus S colon A, or S plus T colon A. And times application, if gamma yields delta S colon A implies B, and gamma yields delta T colon A. From those two, I can derive gamma yields delta S times T colon B. Okay, some basic relationships between the formulations. LP Gensen style proves gamma implies delta if the conjunction of gamma yields the disjunction of delta. That's what we would expect. We could have a system without cut. And we will work without cut for the proof of completeness. Okay, now our main results, arithmetical soundness. If LP proves F, then F star is true under all arithmetical interpretations star. Basic notion of soundness in the theory. Arithmetical completeness. If LP0 does not prove F, then F star is not true for some particular arithmetical interpretation star. In particular, LP proves F if and only if F is valid. I introduced some terms here, arithmetical interpretation. I need to say what that means. So what is an arithmetical interpretation? An arithmetical interpretation is a mapping which takes LP formula to Peano Arithmetic formula in a particular way. We'll define it exactly later, but intuitively I want you to think of the following. T colon F I read as T is a proof of F. So in the mapping I actually want to take it to a real proof of F. T colon F under this mapping should actually map to a real proof of T and F. P we're going to require to be a normal proof predicate. Define what that means in a moment. Star, this interpretation should commute with Booleans as normal. And proof polynomials, how do they map? They will have to map in a particular way as well. We're going to have to take care about how proof polynomials map. Okay, what is this normal proof predicate? What is a proof predicate? It's a provably delta 1 formula pxy such that for every arithmetical sentence theta, PA proves theta if and only if P of n theta holds for some n and omega. And I mean in the standard model. Okay, now a proof predicate is normal. This is like Bu. A proof predicate is normal if it has the following two characteristics. Its proofs are finite. For any set k, the set of theorems which K proves. So K is a proof, L is the code of a theorem it proves. So the set of theorems it proves is finite and computable from K. So our proofs are finite, we're only proving finitely many things, and conjoinable. For any K in L, there's some N which proves all the things that K proved and all the things that N proved. And the way we can formalize this is saying T of K union T of L is contained in some other T of N. And actually, this conjoinability condition implies that normal proof predicates are multiple conclusion ones. Why? Well, see right here. Let's say K proves theta and L proves delta, then N should prove theta and delta. So it's multiple conclusions. Standard proof predicate, which I'll use throughout the talk. Proof of xy if and only if x is the proof of a derivation containing a formula with the code y. Now, important computable functions for proof predicates. You can prove that for every normal proof predicate, there are these three computable functions, m, a, and c, that satisfy the following. If k is a proof of phi implies psi, and n is a proof of psi, I can compute a proof of psi. And this n function right here computes the proof of psi.
So it's encoding modus ponens with numbers.
Basically. If k is a proof of phi, then I can take another number n and produce a phi from that as well. If n is a proof of phi, I can produce a proof ak of n of phi. And if k is a proof of phi, then there is some computable number c of k which proves that k is a proof of phi. So this is proof checker, the last one. Conditions 1 and 3 are related to Hilbert-Bernay's provability conditions. Now we're in a position to define what is an arithmetical interpretation star. An arithmetical interpretation star is the following. Given a normal proof predicate P, along with MA and C just defined, we have to pick a particular MA and C just defined. An arithmetical interpretation is a map from LP to PA that satisfies propositional variables mapped to sentences of PA, proof variables and constants mapped to natural numbers, star commutes with booleans, and the following important relations on these on the proof polynomials. T times S application maps to M of T star S star. T plus S maps to A of T and S. Bang T maps to C of T, and T colon F maps to P of T and F.
Okay. M, A, and C are functions in Peano Arithmetic.
M, A, and C are functions in Peano Arithmetic.
Okay. Now, next page. You finish the sentence. Describes an arithmetical interpretation star of the LP is a map from LP language into PA?
Well, not exactly, because these
yeah.
map to natural numbers. So
fine.
yes,
so
that
fine.
maps
There
to-
maps
yeah, this maps to
natural numbers.
natural numbers. Yeah, it maps to the language of PA.
Yeah, and MA and C are given by delta zero
Formulas?
formulas in PA because they're computable.
They're either delta 0 or delta 1. I believe they're delta 0.
Terms are numbers.
Yeah, they could be delta.
Formulas are formulas.
Terms are numbers and formulas are what?
Arithmetical formulas. Given star, each term becomes a given number of some group. And each formula LP becomes an arithmetical formula, an arithmetical statement about these groups.
Yes, but there is a translation from formulas to numbers which is used in the translation of colon.
Yes. T colon F has a type of a formula. And P of T and what's the right? It's also a formula, but it's an arithmetical formula. Something which can be true or false.
Are you going to tell us what MAC are, or are you, we're just going to know?
This is, later on I'm going to give you a specific MAC when I need to, but for now I'm not going to prove that these exist.
Okay, so we're just taking it they exist, and one day you're going
We're just saying how to use
to,
it.
how it will be used.
And what they actually
What-
are depends on the proof predicate.
Well, I want you to know that a normal proof predicate actually, normal proof predicate with MAC defines the arithmetical interpretation star. So star isn't just given by giving P. When I give you star, then I need to give you P, M, A, and C. And it's possible there's multiple M, A, and C, so I need to specify which ones I'm using.
So point being that once you've given me all that, then using the 4 things on the bottom page, I know how to take any of your
Terms.
formulas and translate them.
Mm-hmm.
If you are really interested in foundations, then if you have P, you can always construct M, A, and C that exist. But since there are multiple choices for M, A, and C, you'd better fix them too. This is a complete picture.
Okay.
Does MA and C stand for anything?
Multiplication, addition, and checker.
Checker, yeah.
Okay, thank you.
Okay, restate the problem. An LP formula F is valid with respect to arithmetical semantics if F star is true under all interpretations star. And it's provably valid if PA proves F star for any star. And our theorem, if LP0 proves F, then F is provably valid, and thus it's valid. Let's go ahead and prove it, as I said, by induction on the formula complexity, and the length of the derivation of F, that is. So first we check all the axioms and inference rules. If F is a tautology of first order logic, well, then F star is a tautology in Peano Arithmetic. So PA proves F star by Gödel's completeness theorem. Next, inductively, how do we build formulas? One way. What is the next axiom? The application axiom. If F is S colon X implies Y, implies T colon X, implies S times T is colon Y. Well, then F star, once you go ahead and you translate it, is written. This is the translation. But this is where the whole point of M comes in, is because actually this is the defining characteristic of M, is that M satisfies this criteria. If S star is a proof of X star implies Y star, and T star is a proof of X star, then M of S star X, S star T star is a proof of Y star. That's what the definition of M was. So this application axiom really is an LP internalization of this fact about normal proof predicates in this computable function. Okay, and it works like that for A as well. S colon X implies S plus T colon X. Well, then S star, proof of S star X star implies a proof of A S star T star is a proof of X star. Okay? Proof checker works the same. Just straight up translation. Verification is the fourth axiom that requires a little bit of work. F star is P of T star X star implies X star. That's when we translate verification axiom. Now P, normal proof predicate, is a delta 1 formula. So PA proves P of T star X star, or PA proves not P of T star X star. In the latter case, then we have the formula trivially. If PA proves the negation of P, then PA proves P T star X star implies X star trivially. If, on the other hand, if PA proves P of T star X star, then P of T star X star holds. Since we're normal proof predicate, PA proves X star. And thus, in this case as well, PA proves P of T star X star implies X star.
I'm sorry. One thing you said there is that P is a delta 1 formula, and MAC was, you said, was a delta 0, probably a delta 0? Why is it stronger? Why is it harder?
Well, a proof predicate, it is typically a delta 1 formula. You run, how does a proof predicate work? Well, you run a search. How could I prove that something's true? Is I could list a particular sequence of formulas, And I could go ahead and I could check one by one whether or not that the sequence,
So for
matched
every
it.
formula, the next one, it's a consequence of the previous one.
yeah,
So that's a delta, that's a, okay. That's not delta, that's a pi one.
that's pi 1. But if it's false, we can, if it's false, then it's also, we can show at some point that it's false. So the negation of it will also
So
be,
it's both
Okay.
delta 1 and, so it's both.
it's sigma 1 and pi 1.
Okay.
This is the definition of delta 1.
Modus ponens hold for normal proof predicates, that's a fact, standard fact. Okay, and since the only theorems of LP0 axioms are obtained by modus ponens, this proves soundness. All right, now completeness. If f is valid, then LP0 proves f. This is the hard one. How are we going to do this? We're going to argue the contrapositive. We're going to say if LP0 does not prove f, we're going to create something called a completed and saturated sequent. I'll explain what that is. Based on this particular completed saturated sequent, I'm going to define a specific interpretation star. And star is going to contain our formula f inside of delta. I'm sorry, I should have mentioned that. F is in delta. We're going to define this interpretation star. Then in this particular interpretation star, PA proves x star for all x and gamma, and it proves delta. It proves the negation of x for all x and delta. So in particular, PA proves not f star, since it's in delta. And then all we have to do is show that star is an arithmetical interpretation, which is going to require some work. Okay, what is a saturated sequent? A saturated sequent is a sequent essentially which is closed under subformulae. If A implies B is in gamma, then A is in delta or B is in gamma. If A or B is in delta, then A is in gamma and B is in delta. And there's a number of conditions right here. I'll skip all the conditions, just a little bit of a formalism, but I want you to have the intuition that this is closed under subformula.
So it's similar to a transitive set, but you divide it up among the sides based on
Particular conditions.
compatibility conditions, yeah.
Now, the saturation lemma, if we have an unprovable sequent, then there exists a saturated sequent which extends our unprovable sequent and which also is unprovable. So if gamma implies delta, I can extend gamma, I can extend delta to gamma prime and delta prime. This is saturated and it's still unprovable. How do you prove this? Well, you perform a saturation algorithm on gamma implies delta, which is a standard procedure in proof theory. Each leaf node will be a saturated sequent, and for each step in the algorithm, if all the children are derivable, the parent is derivable. Since our original sequent, gamma implies delta, was not derivable, this means at least one leaf node is not derivable, which means at least one saturated sequent is not derivable. So we have a saturated sequent which is not derivable. Moreover, we can actually say more about it. We can show that this saturated sequent, gamma and delta, are disjoint. This is an example of a saturated sequent. You perform a saturation algorithm. Each step you add more formulas. Sometimes you branch. And all of these are leaf nodes. They're all saturated. One of them is not provable because the base is not provable. Okay, completion lemma. We have what is a completed sequent? Well, a completed sequent is, now I want you to think a completed sequent is we close on the LP axioms. We close under application. If S is a proof that X implies Y, and T is a proof of X, then S times T is a proof of Y. And this should be in gamma. If T is a proof of X in gamma, then bang T is a proof that T is a proof of X is in gamma. And similarly, we close under choice. So gamma tilde, I should say, extends gamma, and it's closed in the LP axioms. And it's also closed downwards in this sense. If T colon A is in gamma, then A is in gamma tilde. And it's provably decidable. This is this is also a very important property. For each t, set of x, such that t colon x is in gamma, is finite and computable from t. Now what does this mean? T colon x is, t is a proof of x. So for each t, the set of x is, that t colon x in gamma is finite. So for each t, the things which t proves is finite and computable in gamma. You can create an algorithm. One creates an algorithm to prove that a completion exists. At levels, you introduce application. At another level, you introduce proof checker. At another level, you introduce choice. And you take the union over all of these. And this one can show that this is finite. We still maintain finite and computable from t. So it's a technical detail.
But it's only finite for particular t's, not for, the whole thing is infinite though?
The whole set is infinite, but for each particular t, it's finite. For each particular t, the set of theorems that t is a proof of, the set of formulas t is a proof of, is finite.
So this LPG calculus still kind of works as an infinitary logic?
I haven't seen any information about LP applied to infinitary logic. This is sort of like a finite
We're
system.
building a model, and the model is necessarily infinite, but the logic itself is finite.
Yeah, we have finite conjunctions and disjunctions. We prove everything proves, every proof, polynomial, is a proof of a finite number of objects. So we're
Okay,
dealing with a finite thing.
at the point that you're dealing with here, you don't have to make sense of this particular sequence as a logical object anymore. You're getting close to the arithmetical end of this.
Oh, I see. So you're talking about, this isn't a finite sequent anymore.
Yeah.
The sequent is not finite. Gamma is no longer finite. Now, completeness. Let's define that star I was talking about in the following way. It's going to require a few steps. Suppose LP0 does not prove F, then we have LPG does not prove empty sequent F. F is in our delta. We saturate and complete empty sequent F to obtain this saturated and complete sequent gamma sequent delta. Gamma implies delta. Now based on this sequent, we're going to define star as follows, and in stages. We have a Gödel numbering, first of all, and this Gödel numbering is injective and non-zero. So if S is in gamma in a propositional letter, then set S star equal to the code of S equals the code of S. This is true. So basically, if S is in gamma, then set S equal to true. If S is not in gamma, since our coding is non-zero, set S star equal to code of S equals 0. In other words, if S is not in gamma, set S star equal to false. Proof variables and proof constants map to their own codes. And times plus bang and colon all map to M, A, and C and PRF as we were required. But we're going to define these in a little bit. We're not in a position to define them yet. We have to first introduce an intermediate translation, Dagger. Now what is Dagger? It's an intermediate translation. It's based on a formula P. May or may not be a proof predicate, just a two variable proof arithmetical formula. So S dagger is S star for all propositional letters. T dagger is the code of T for proof polynomials. T colon F dagger is P of T dagger F dagger. And dagger can be used with booleans. Now our PRF, our proof, our PRF that we're going to define, our proof predicate, is going to be a fixed point of this. It's going to involve a fixed point equation. So it's like PRF of xy if and only if phi of dagger PRF xy. So this is a fixed point. PRF on the left, PRF on the right. Define an equation. This means PRF is the result of a fixed point equation. And we can have such a fixed point. So given any formula f of 3 free variables, there exists a formula of 2 free variables such that PA of AXY if and only if f of AXY, XY. So this is just your standard fixed point theorem, except now instead, usually you see it as a sentence on the left. Now I'm saying it has 2 free variables. And here is the fixed point equation. All of the top is this is the actual formula for it. But what I want you to look at is the intuition behind PRF right down at the bottom. What does PRF say? This is our normal proof predicate. PRF of xy if and only if x proof of xy. So PRF will hold if and only if x is a real proof of y, the standard proof of y, or x is the code of t for some proof polynomial t, y is b dagger PRF for some b and it. And b and it is the same as saying t colon b is in gamma. Okay? So PRF, if and only if we're a real proof, or the following, or t colon b is in gamma. T is a proof that b of b. And notice PRF on the left, PRF on the right, that's a fixed point equation. Okay, some intuition about this, the meaning of the fixed point equation. It's a little bit opaque. When does this hold? Well, given that I of t is set of x such that t colon x is in gamma, PRF will hold in 2 cases. It'll hold for n of phi if actually n is a proof of phi, like a real one. Or it'll hold in the case where we have t and b dagger for t colon b in gamma. These are the conditions. We're going to need to define MA and C for star. And to do so, we're going to rely on the fact that proof is a normal proof predicate. So it has associated its own M, A, and C. Those letters are taken, so I'm going to call them time cross, plus, and up arrow. These are the associated M, A, and C for proof. And without loss of generality, we can assume that proof is false for any proof polynomial t. Okay, so now I produce the M, A, and C. This formula is big, so let me try to explain what it means here. N will be the least z such that the following condition holds. M of x, y, z holds. Now, if x and t, I'm sorry, if x and y are both codes of proof polynomials, then just output s times t. So if x is s and y is t for proof polynomials, output the code of s times t. On the other hand, if they're not proof polynomials, then they should probably be real proofs. And in that case, I'm going to have x times y, because that's what the real proof does. Now the 2 middle cases are symmetric cases where we have a proof polynomial and we don't have a proof polynomial. If we don't have a proof polynomial, I wrote down a little notes to explain this for myself. So, okay, so let's look at this. B, if x is s for a proof polynomial and y is not any proof polynomial for t, then we should output v, where v is the least w, such that w proves b dagger for all b and is. So s colon b is in gamma. Gamma thinks that s is a proof of b. So w should be a proof of everything that s is a proof of. That's what we're saying here. W is a proof that of everything that s is a proof of when we make the appropriate translations between proof polynomials. And this actually is a real-life proof. So in this sense, what we're doing here is we're taking something which was x is s, so we're taking something which was related to x in the LP language, and we're converting it into a real piano proof.
By doing a proof search?
Kind of like that, yeah. We're doing a proof search. we're looking at everything. The proof search occurs here. B is an IS. We look at everything. All B, which is an IS, are all the theorems B, which S proves. We take those theorems, we translate them, we make sure we prove all of them, and that's what we output. So
What if there isn't such a proof?
if there isn't such a proof, then you could output 0. But in the end, this actually there will be such a proof, and I can show that for what we're looking for.
Interesting.
A is similarly defined, except we're using plus operations. Same idea. And C is also similarly defined. This last statement is a little bit different looking, but for the sake of time, I'm going to skip over that. Okay, now, we're in a position to show that star actually equals dagger. This is an intermediate translation, but actually they're the same thing. And we proved by induction on induction. So, let's check star applied to S times T. S times T star is M of T star S star. Now, by induction hypothesis, M of T dagger, this is M of T dagger S dagger. By induction hypothesis, T and S, T star equals T dagger by induction hypothesis. So T dagger, remember, is the code of T. So now this equals M of code of T S of T. Now what happens when you have the code of T, M of code of T S of T for proof polynomials? You output the code of T times S. The code of T times S is T times S dagger. So we can check it on PRF as well. T colon F star is PRF of T star F star. Induction hypothesis, PRF T dagger F dagger, just T colon F dagger. And in the base case, forgot to mention, they agree because they agree on variables, constants, and proof polynomials. It's just the code, the Gauss code. And one can show by induction that they're also equivalent on formula as well, not just terms. So star and dagger agree, and they're actually the same thing. Now, we've done a lot of work up until now. We haven't actually proved much, so thank you for listening. Now let's prove something. Let's prove this important property. If x is in gamma, then PA proves x star. If x is in delta, then PA proves the negation of x star. Intuitively, we think of gamma as true and delta as false. How do we prove it? Well, by induction on formula complexity. If x is atomic, PA proves x star if and only if x is in gamma. Because remember, if x is in gamma and it's atomic, then x star basically maps to x star equals x star, true. And if we were not in gamma, remember the condition, we map to x star equals 0, which is false. So if PA is not in gamma, then we map to false. So PA proves the negation of x star in that case. And since delta is disjoint from gamma, this proves the base case. Induction step for the colon operator. Let x equal t colon f. So what is x star? It's PRF of t f star. Now, two cases. If x is in gamma or if x is in delta. If x is in gamma, then PA proves that f is in I of t. Remember, because it's computable, it's decidable. So thus, based on the condition for PRF, PA proves PRF of t f dagger. And now since f dagger equals f star, PA proves PRF of t f star. And that is PA proves t colon f star. On the other hand, if x is in delta, then decidedly f is not in IT. Why not? Otherwise, t colon f would be in gamma. Then by the fixed point equation, otherwise t colon f would be in gamma. We just said t colon f is in delta. Okay, so by the fixed point equation, how could PRF of TF star hold? Well, the only other way it could hold is if we have proof of TF star. But proof actually is false for any proof polynomial. And it's provably false for any proof polynomial. And that's, in this case as well, PA proves the negation of PRF TF star. So induction steps corresponding to Booleans follow from the saturation properties. So this is nice. P8 proves x star if x is in gamma, and P8 proves the negation of x star if x is in delta. Remember what we started off with? We started off with an unprovable formula. We made sure it was in a completed and saturated sequence where it still lived in delta. So now we're in a position where P8 proves the negation of f star. We don't have that star is an arithmetical interpretation, however. We don't even have that PRF as a proof predicate, but now we do. Proof, well, suppose P8 proves C, then P8 proves proof of Cape C, so P8 proves PRF of Cape C. Now on the other hand, suppose PRF holds for some n in omega. On the one hand, we could have that as proof of n C holds. Then P8 proves C. Otherwise, by fixed point, C is F dagger for some LP formula F, n is T for some proof polynomial T, and F is in IT. Then we have T colon F is in gamma. Since gamma is complete, this means F is in gamma. And from the previous lemma, since F is in gamma, P8 proves F star. And F star is C. So this means that PRF is a proof predicate. PRF is a proof predicate, star is some kind of interpretation on LP based on PRF in this sequence, and P8 proves the negation of F star. We need to show that PRF is normal, whereby it'll follow that star is an arithmetical interpretation. Okay, so what do we need to do? What we really need to show is that PRF satisfies these M, A, and C. This is the same slide as I showed you before. For a normal proof predicate, it obeys these M, A, and C formula. I just need to show that this holds for PRF in particular. But actually, before I prove it, I want to show that choice, the second and third one, choice is all that we need to show that PRF is normal. All four together give us that we have an arithmetical interpretation of LP. So let me show that. If PRF respects choice, then PRF proofs are conjoinable. Why? Well, remember what it means to be conjoinable. It means Tx union Ty is contained in some other thing. So T of K is L, PRF KL. And if we have choice, the first line holds since we have choice. And this means that T of X is contained in T of AXY. The things which X proves, AXY also proves. By symmetry, the things that Y proves, AXY also proves. And therefore, the things that X proves, union the things that Y proves, is contained in the things that AXY proves. So choice gives us conjoinability. Choice also gives us that the proofs are finite. We only prove a finite number of things for each proof polynomial. Well, why? How could PRF KL hold? We need this set TK to be finite. It could hold if proof KL holds. Now proof is a normal, so we appeal to the normality of proof. On the other hand, if K is S for a proof polynomial, IS is finite, and so is T of K. Because T of K now is T of the code of S, and based on the condition for PRF, this is T of S is just X dagger, where S colon X is in gamma. And look, we have one-to-one mapping from T and I now. Since I is finite, T is finite. And we construct such an algorithm taking K to T of K. Okay, so if we get choice, then proof is a normal proof predicate. PRF is a normal proof predicate. We need to show arithmetical interpretation. Yes, so Y, it's delta 1. It's a proof predicate, finite and conjoinable. Now, if we have all four, then we're in a position of star as an arithmetical interpretation. Why? Because it maps Booleans appropriately, PRF is normal, and because MA and C behave correctly with respect to proof. Now notice, how could PRF hold? So we're running a little bit, I'm looking at the clock right now, and the proof that MA and C behave correctly with respect to proof is possible, but in the interest of giving a little bit more higher level talk, more conceptual, I want to gloss over that and talk about the relationship to BHK. Okay. So basically, I want you to know that how do we prove this? And we prove it based on cases. We prove if x is a proof polynomial or not, if y is a proof polynomial or not. And you prove it based on the cases. Okay?
And miraculously all the ends meet.
Miraculously, all the ends meet. It's a nice technical proof. Okay, well, let's finish. Let's say we have that. Let's finish our plate. If LP does not prove F, then F star is false for some arithmetical interpretation star. Why? Suppose LP0 does not prove F, then LP0G does not prove empty sequent F, saturated and completed, so F is in delta for some saturated and complete gamma sequent delta. We can define star based on this. It's a normal proof. It's an arithmetical interpretation with F in delta. Since F is in delta, PA proves not F star. And combining completeness and soundness, we have LP proves F if and only if F is valid with respect to arithmetical semantics. Okay, so that's a completeness proof. Now I want to talk about the BHK. Let's see, how does LP actually discuss, what does LP have to say about BHK? And we'll go step by step. There are 4 clauses for BHK. A proof of A and B consists of a proof of proposition A and a proof of proposition B. How could I reword this? Well, given a proof T of A and B, I want to have a uniform way to demonstrate automatically a proof of A, a proof U of A, and a proof V of B. Presumably they should depend on our original proof. Okay, suppose T is an LP proof of A and B, then we have T colon A and B. And I want to produce terms in LP, U of T and V of T. U of T colon A, U of T is a proof of A, and V of T is a proof of B. And I do it through the LP reasoning. We're working in LP now. Axiom, A and B implies A. Constant specification, I can apply axiom necessitation. C1 colon A and B implies A by axiom necessitation. T is a proof of A and B, T colon A and B by assumption. And then I take application. If C1 is a proof of A and B implies A, and T is a proof of A and B, then T times C1 is a proof of A. So there we got it. U of T is T times C1. I got our proof of A. And similarly, you do the same thing. C2 is A and B implies B. T times C2 is a proof of B. So already we see that contained in a proof of A and B existed a proof of A and existed a proof of B. We were able to unravel a proof of A and a proof of B.
What about the other way around?
Given a proof of A and given a proof of B, could we produce a proof of A and B? That's something that I was thinking about. I couldn't demonstrate it to myself, though.
You can cook up something right away on the code. You still remember how to.
Let's check out these other guys first, and we can come back to that. A proof of A or B consists of proof of proposition A or proof of proposition B. And what does this mean? Suppose we have a proof of T. Could we provide a proof T can we provide a uniform way to provide a proof U of T such that if T is a proof of A or T is a proof of B, then U of T is a proof of A or B. So if T is a proof of A or T is a proof of B, either case I can produce a proof of A or B. Now we can. Suppose we do it by cases. Shoot, this is a big typo up there. Suppose T is colon proof A and B. So forget this line. We have A implies A or B, constant axiom necessitation. C colon A implies A or B. We also have axiom B implies A or B, because it's just an axiom, it's a tautology. So axiom necessitation C2 is the proof of B implies A or B. Now set U of T to be T times C1 plus T times C2. Why? Okay, now suppose T is a proof of A. I meant to say suppose T is a proof of A or T is a proof of B in English. So suppose T is a proof of A. Then T times C1 is a proof of A or B by application. And then by choice, T times C1 plus T times C2 is a proof of A or B. And similarly, if T is a proof of B, I take C2 and I do T times C2 to get rid of this B, and I have T times C2 as a proof of A or B. And I add them up and I get T times C1 plus T times C2 as a proof of A or B. In either case, I get T times C1 plus T times C2 as a proof of A or B. So that's nice for OR.
Okay, so I answered my first question for the other way around, but now I have the
Opposite question.
now I have the opposite question, and it seems even harder.
It does seem even harder. This one I was also troubled with as well. Given a proof, but notice the language here is I was thinking about that, but notice the language is different. Here it says a proof consists of a proof. To me that means that there's already contained in the proof of A and B a proof of A and a proof of B. We don't use the word consist. Oops, we do.
Yes.
Yes. Some language, that's a problem. A proof of A or B is demonstrated by giving a proposition A or a proposition B.
Since you insist.
We insist.
What do you want to do, conjunction?
Let's do disjunction, it's harder.
Okay, so what do you want from disjunction?
The ability to, given a proof of A or B,
Yes.
I want to either have a proof of A or a proof of B.
You can't do that actually, because you could have a proof of A or not A, because that's an axiom. And then T colon A or not A. T is a proof of A or not A. But that's not, so we can't give a proof of A or a proof of not A automatically. So how does it relate to intuitionism?
Yeah, that's the question.
Yeah.
Yes.
I can answer your previous question because it's just the conjunction. Then, okay, I'll
Yes,
do this.
let's answer the previous question.
Let's do the previous question because that's what I came with. So this because it's just. So okay, so we want X to be a proof of A and Y is a proof of B, and we want to cook the term T X Y, which will be the proof of A and B. Yes. Well, within the tools of LP. Okay. We take the propositional axiom, which governs the behavior of conjunction. Since it's an axiom, we have an incitation rule, so there is a constant C. We internalize this axiom with some, just nominate a constant to be a proof of the whole thing. Now, we have concentrate on this implication. So the C is a, you remember the application axiom. If C is a proof of implication, then whatever is a proof of antecedent, C implied to this one gives the proof of succeedent. Yes. So you do this, if X, it's one-step proof, is a proof of A, then C times X would be a proof of the thing, the succeedent. Yes. B implies and B. We need one more step. Gain the application. And it goes the right order because it's in a positive position, and it tells that for this particular implication, if we have a proof of implication that whatever is a proof of B, this proof of B being inputs of this one will give you the proof of the. So we pick Y, of course. So this part remains as is. And for this one, we'll have, if Y is a proof of B, then C times X, now it's times Y, will be the proof of A and B. I have to close. This is the one. This is T, excuse me, TXY. Which we wanted to have. And we have the similar solution for disjunction, but let me, if you want, give the speaker, I suggest, give the speaker, finish the talk, and then I promise I will give you the answer.
Thank you.
Okay, so this is a good question, and maybe come back to it, either before or after 9 p.m. Now, let's talk about negation. There's a little bit of trouble with negation. Let's look at how we actually phrase negation. The proof of A implies B is a construction transforming proofs of A into proofs of B. And falsehood is a proposition which has no proof. So what is not A, but it's A implies falsehood. What this means is a proof of A yields a proof of falsehood. However, there is no such proof of falsehood. Actually, let's put it another way. Suppose not A is constructively true. So we have a BHK proof. So there is no proof of A. Why? Because if there was a proof of A, then we could get a proof of falsehood. Since there is no proof of A, this holds trivially. The negation, this implication holds trivially. There is no proof of the antecedent, therefore the whole implication holds trivially. In other words, assuming that not A is constructively true,
You could be king.
yeah, you can get whatever you want. You can prove whatever you want on the right-hand side. And so this is curious. There really had nothing, there was no relation between this proof of falsehood right here. So we don't want this, and so then, since there's no proof of A, the condition on not A holds trivially, then any construction which fits the appropriate format would be a proof of not A. Because, well, it fits the format. Antecedent holds trivially. So this is the problem. Now let's see what happens if we do the BH, if we actually first take negation, put it into S4, and then take the LP realization of that. Consider not A with A atomic for notational simplicity. The Gödel translation of not A into S4, box every subformula. It's box, not box A. We didn't talk about the realization of LP into PA. I'm sorry, of S4 into LP. But the way it works is negative occurrences of box get functions of X, and positive get variables. So we're going to get is P of X colon not X colon A. This is how it should be realized in LP. And what this says is for any proof term X, P of X is a proof that X is not a proof of A. And this is really the desired semantics. This is the improved semantics for negation. So we have an actual construction P which says X is not a proof of A for every X. Okay. Now, implication. A proof of A implies B is a construction transform proofs of A into proofs of B. The problems with negation also holds, it's a specific instance for a problem with implication in general, because as was pointed out, I could put anything. I don't need to put a falsum on the right-hand side. If A is constructively false, it has no proof, then I could put anything right here, and it'll be, this implication will hold. So that's a specific case. Now, another one, consider how one often reasons in classical logic. Here it goes. How would you prove A? Well, first you have the axiom A implies B implies A, and you have apply A implies B, and from modus ponens, you get A. So a proof of A itself, we often use things which contained A. Now, if we were to use the traditional reading of BHK proof, a proof of A implies B is a construction which, given a proof of A, yields a proof of B, there's a sort of impredicativity going on here. Because to prove A to begin with, we had to have constructions involving A implies B. And we also had to have constructions involving A. So this is impredicativity, which is hard to build in a ground-up kind of way. Especially, it's hard to square with your traditional PA proof predicate, in particular with its monotonic Gödel numbering. So it's hard to have, if the Gödel numbering just keeps going up every time you apply an implication, then how could you have this be a proof of A? So, what do we do? Well, Kreisel in the 60s, he came up with the second clause for this. He said, well, yep, it's a proof A implies B because the construction transforms any proof A into proof B, and with a proof that this construction satisfies the desired property. In other words, we have the original x colon A implies cube x colon B, but we also can prove it. This is what Kreisel said. Now, let's consider BHK semantics in LP. Again, taking the Gödel translation. A implies B in S4 is box A implies box B. And in LP, this gets realized as P of x colon A implies cube x colon B. Just flashback, that's Kreisel's condition. So LP realizes A implies B as Kreisel's second clause. We say a proof of A implies B is a pair of P and Q such that for each x, if x is a proof of A, I can generate Q, which is a proof of B. And moreover, P is a witness that proves this implication holds. And I was also talking about the impredicativity. That's not a problem for LP. LP allows self-referential proofs, like I wrote down here. T is a proof that S of T is a proof of A. In fact, you need it to prove certain theorems. And PRF, it's a fixed point equation. So it, of course, should allow some sort of self-reference. Okay? So that's, so the conclusion is, what we did today was we demonstrated that there's a sequence of embeddings. Intuitionistic propositional calculus embeds into S4, S4 embeds into LP, and LP embeds into PA. We proved the last embedding, and we also showed at the end that LP provides a semantics for LP. LP provides a semantics for IPC. The semantics respects BHK semantics for IPC after closing the loopholes in compliance with Kreisel's second clause. And the BHK proofs in LP are interpreted in PA as actual arithmetical proofs. So we actually do the job. We said we wanted a real proof, and we produced a real proof. So that's it. Thank you guys for listening.
Any questions? Any attacks?
The other question for James that was postponed.
About the disjunction? So I was thinking about disjunction.
I'm ready to answer.
Are you ready to answer?
You had a lot of classes today, so I can just, I know that you will. Okay.
All right.
Also, I can take a sheet for.
Hey, you want to wait till after, or you want to try to take?
Well, I don't care. The book is about to come within a couple of months in Cambridge.
Yeah, I was going to ask where this is written up because
Okay,
there
sure.
was no way I could write this on, read
I
this
have
in
it.
real time.
Yeah, there's reference slide as well. I'll give it to you.
So questions, any more questions?
Well, this was for
I have
writing
a
down.
comment, but I'll wait till you're done, because it's,
Yeah.
Here's references,
more relevant.
Okay.
and I'll put that on the end, but if you want, just so people know, I'll show the
Okay.
I wanted to see the reference again.
references.
Yeah, leave it at the references. Let me.
Look, in the BHK environment, we're not talking about arbitrary A's and B's. They're themselves boxed because there are claims about proofs. Because each of them, it's not just a proposition, or even it's a proposition, it's interpreted. So let me write it down in the model language first. In the model language, you would say, we have, because we'll populate the boxes afterwards, but model language is a schematic language. It's very good to make a point. So the real format of when we apply this is box A or box B, where now A and B are more or less arbitrary. Or something but they are supposed to be boxed. Otherwise, this is a general thing, and this one will go a little bit deeper. We'll play on the real format of the problem at hand. Once you have this well, the corresponding thing you want, and this is, it's A prime, where A is box A prime, and B is box B prime. All right. Now, I still want to have T of X as a proof of A. So then I want so I want to have a box. I will populate this box with what I want, but it's the format thing first. Of A and A is box A prime. Box A prime, and this is or box B prime. So this is a real format of what we want to populate. Now, this thing is provable in this form. I can immediately do it, just hand waving, or just if you wish, 3 minutes of formal derivation. But basically it says, because here's a derivation. You take this box, then by factivity or reflexivity, this thing is, it's easier to prove. Okay, proving this thing. When I prove this, I do realization, or if you wish, we can, is it okay if I show you that this T and S exist? Because writing them up is maybe a little bit, too much in the 10th after 9 o'clock. But okay, so first of all, this thing is provable in S4, because this box A prime or box B prime yields box A prime or box B prime just because of the factivity. Now, by proof checking, this one yields double box A prime, and this one yields double box B prime. So this proves this one, that's 4, yes? And then you just run realization. The realization algorithm populates all the boxes. This is the missing part, which was the realization. It fills all the negative boxes with negative. There are negations of essential quantifier. It means there are universal quantifier. Universal quantifiers are all realized by Scollum style. They're realized with variables, and positive boxes are realized by functions of those variables. That's what the realization algorithm delivers. It means that just from a realization algorithm, these are both positive ones, and these are all negative ones. It means that if we have X, Y, and Z, then they're all negative parts. So if X is a proof that Y is a proof of A and Z, or Z is a proof of B, then I can build T1 of all three, T2, A prime. I should do better. I should just say this Y. I can do Y.
I think part of this is that T1 and the corresponding one for Z are probably going to just be CT1 and C.
Yeah,
or CY.
Oh yes,
So they're actually independent of X.
Yes, this can happen. So it means that they exist uniformly, regardless of X, because the A and B themselves define the whole thing.
Okay, so in this case, the
Very good.
the translation of propositional calculus into S4 does the work of satisfying the BHK semantics. Because it's not.
The translation. Tell me what. So just to repeat the first part of the sentence.
Okay, the translation of IPC into
IPC,
S4.
yes. Yeah. Yep. And that's by the way the Gödel translation. And by boxing the whole thing, it means that if this is an intuitionistic statement, then whenever I parse it and trying to make a semantic sense of it, whenever the classical algorithm says, well, disjunction is true if one of the disjuncts is true, I have to say disjunction is provable if one of the disjuncts is provable, religiously following Brouwer's recipe, replacing truth by provable. This immediately defines, with a laser precision, the syntactic translation which Gödel suggested. Box every subformula. And you take intuitionistic formula, box every each subformula, you end up with a classical sentence with a lot of boxes. But if box is probability, that's what you make sense. That's how we make a classical sense out of Brouwer's nonsense. That was a Gödel approach. He didn't quite embrace intuition from the beginning. He wanted to explain it from the classical point of view, and that was his answer. In this respect, yes, I agree. Gödel himself, there is a famous quote of him saying that I defined Intuitionism within the classical logic with the notion of probability. Good. Yes.
So I'm just curious. So in this case, disjunction, so we needed boxes in front of propositional letters.
Yeah.
But in the case of conjunction, we didn't need that. But given the semantics of BHK, then it seems more proper to populate the formula with boxes too. And I
absolutely,
think
absolutely. I just gave you a less muddy picture because this reasoning goes in a more general situation, so we just don't care about. But to be consistent with the presentation, we have to have these things are also. But there will be a lot of columns, a lot of boxes, which I spared you.
And it's actually an interesting fact that for things that fall into the fragment of minimal logic, you don't need to do the boxes to actually have the BHK semantics.
Yeah. Well, this is the Gödel. There are many ways to trying to make sense of BHK, and I just don't want to listen. I don't want to lecture about what's the type theory is and what is the Martin-Löf type theory is, and so what's intrinsic. We have experts who can do it. Yes, yeah, absolutely. Yeah. But this is a Gödelian way. Just we made sense of what Gödel designed as a first attempt to make sense of BHK in the 1933, and then the whole effort stalled for almost 60 years, for 60 plus years, because people learned how to handle the formal proof and probability logical proof, and after we sorted out technical things, we just did it because it's not that the proof is too long, but it's extremely heavy in keeping track of what you know at the moment, what you don't, and then winding all these deductions. So you need to have some sense of direction, otherwise the answer will not be. Okay?
Or just a quicker thing, make the slides available somewhere, or?
Sure, I can email Professor Yanowski, and would you be able to distribute it to everybody?
No, I'm going to put it on the YouTube page as a link in the YouTube page.
All right, fine.
Gershom, you had a point?
I'll hold off. It's all the stuff he just said he didn't want to talk about, so I'll just mention it later.
I just have one, is there any relationship with this and HOTT? I mean, seriously, it's you're both dealing with the same thing. You're proofs of things and how you construct proofs.
John, can you?
I have no idea.
He's too modest.
Yeah, I
He's
would
too
have asked
modest.
about
He's too modest.
realizability.
Well, that's what I was going to mention is Dana Scott has been lecturing for the last few years. You know, he's very emeritus, but on this lovely model that is called he calls the power set of the naturals model. I don't know if you and it seems, you know, it's not exact, but sort of a modern revisiting of the sort of classic realizability semantics, where he gets this sort of where he gives a topology or has a nice natural topology in the power set of the naturals, and then he sort of combines that with a bit of recursion theory, and then even though he goes via dependent type theory rather than sort of via this classical modal logic, you know, he ends up with something extremely arithmetical at the end that has sort of a version of this proof search element, because it involves walking through this power set enumeration to do it. So it seemed like it was just worth mentioning. I didn't have anything deeper to say, except it's a very elegant model. And I don't think he's written it up in any published paper, because he doesn't do that anymore. But there's a million slides and talks of him on the web presenting it.
So answering your question, that people think about it, because that's that's one of the most intriguing questions in the field. But you really have to be a little bit synthetic. You have to be Leonardo. You have to know in intimate details several fields, and then so people are learning. We're studying this question, so it's not.
I think we should thank our speaker again.
Thank you.